from the above or you can take it from the bottom. That's a camera pose. It's an XYZ coordinate, or it can also be described by the polar coordinate, which is sine and cosine, in relation to an origin. Line position, again, just literally a XYZ coordinate in the 3D space.
So camera pose and line position, it represented by a vector, right?
Yeah. So given that information, you first transform the object to the pose that you want, so that you can have the picture from the pose that you want. You use the 3D of convolutions to learn perspective morphing. And then we have the projection unit, which is where we try to learn the visibility step that backtrack a bit. Visibility is the step that calls the indifferentiability, right? 0, 1 step function. Now we try to learn a function that tries to approximate that, but differentiable. So here, we make a conscious design effort to design a projection unit where we use an MLP, a multiple layer perceptron, to learn this step. So the input to this projection unit is still a 3D feature. So you have height. Sorry, I don't have a pointer, but let's look at the dimension 32, 32, 32, 16. So that's the input. So it's basically height, width, and depth, and the feature channel. So that's the input. It's a 3D. The output is only 32 by 32 by 512. So basically, it dropped one dimension. That's what projection does, right? We use an MLP to learn this operation to make it differentiable. So, so you can treat the first part, the yellow 3D convolution part, and the projection unit as computing visibility. Remember that step rendering? That's the part that computing the visibility. And the 2D convolution, like typical 2D convolution, is the part that compute the 2D, the shading. So what is the actual color of each pixel look like? And so that is the design, and we just train this using mean square error loss. So this is a supervised problem. And oops, I'm supposed to go through each of them, but I've already done that. So yeah, just a mean square error loss. So this is a deterministic function, learn function, and yeah. So this is a closer look of the projection unit. So the input again is a 3D tensor, height, width, and depth, and channel. You first concatenating, literally like concatenating the depth and the feature channel together. So here you have the drop of dimension from 4 to 3, and then you use the MLP to learn the visibility throughout the whole depth, and then you have the 2D tensor coming out. So that's basically the model. So when we design this model, we on purpose try to recreate the rendering pipeline from the computer graphics. So we have a combination of both 3D convolutions to learn anything to do with depth dimension, and 2D convolution to learn anything to do with like colors and things like that. And that makes a huge difference. And the fact that we don't force the network to do rotation makes a huge difference as well. And I'm going to show that in a minute. So here's the training data. So I use ShapeNet, which is currently the biggest 3D models data set publicly available that can be used by researchers. And within that data set, we use the chair category, which again has the most models that we can use, because you want more data, you want more variation in geometry, so chairs can look very different, right? And you want that variability in the geometry. So that's and then we render them in different shaders, so different style of rendering, and to see whether the network can learn different style of rendering or not. So that's the training data. So if this is the input, so you have a bunch of chairs. This is relatively low resolution, it's 64Q binary voxels. So the first shaders, the first rendering style that we learned is the foam shading. So this is the most popular shaders you can find. Any 3D modeling software will use shading as a testing shading. We can learn what we call non-photorealistic or stylistic rendering style as well. So because we don't handcraft the rendering part, we can use the same work to learn any style that we want, basically, in contrast to the previous state of the art. You can learn a toon shading, which is a composite between, between line drawings and the toon shaders. And the most interesting part is ambient occlusion. So ambient occlusion used to be done by ray tracing, which takes a while to generate an image. But now, because once we train a network, it's just a matter of a feed-forward testing. So using the same design, we can learn any different style of shaders, and it can greatly speed up the rendering time as well. So that's a plus. For me, the most interesting part is actually this part. So this model was trained on chairs because, again, that is the biggest data set that we have. But once it's trained on chairs, it can render any other objects as well. So here we try to render the Stanford bunny, as I mentioned, and again, this is interesting because if you look at all of the generative models we've seen, all of the computer vision models we've seen, if you train it on cats, then it can generate cat's picture. If you train it on dogs, you can generate dog's picture. But this ability to generalize across different categories is quite interesting. So that is good. To push it a bit further, what I did is that I take the model of the bunny and I corrupt it. I add some random noise to it to see how it can deal with like unsmooth surface. I also downsampled it so that it's much lower resolution, so the model looks like very blocky, and just want to see how the model deals with it. What we realized is that this model, in addition to rendering, it also does some sort of super resolution, in the sense that even if you give it a very blocky model, it can still generate a very smooth rendering image out. So that's interesting to see. And if any of you have tried with meshes before, like render with mesh is, I really don't like mesh because they are, although it's very compact, it's very, very sensitive. In a way that if you have a mesh that is not clean, which if it has double surface, if it has a hole, if it has a ragged edge, then the model will feel like a normal rendering pipeline will render very rubbish image. But with this model, because it's also doing some sort of super resolution, it can deal with corrupted models as well, which is a huge advantage. So that's good. And again, when we train this model, we train it on chair. So we train it on a single object, right? Just a chair in the middle of the scene. But it can also render scenes with multiple objects, because and this really shows that it really learns how to compute visibility. Because when you start to have multiple objects, then occlusion becomes a bigger problem, right? And only when you can learn, only when